Okay, I hope everybody had a good day today. Tonight we're going to continue our first week of study, and we're going to be focusing on some of the fundamentals of voltage and current principles. There are some basic definitions that are paramount to your understanding electrical engineering technology, electronics, electrical engineering, whichever field you go into. Each one of those areas are somewhat misunderstood by people that are even in the trade. Okay? And so what I'd like to do is I'd like to start off by talking about a quantity that is somewhat misunderstood, and I'd like to make an analogy for you to a mechanical situation that really represents the same thing that's happening in an electrical circuit. One of the fundamental principles that we're going to be studying in this course and throughout your entire career you're going to be using is the concept of resistance. Resistance is a quantity that's measured in ohms. This is just the Greek symbol that's used to designate ohms, but I'll write ohms just to make clear that that's what we're talking about. When I was first introduced to ohms, I had a misunderstanding about how ohms really worked in an electrical circuit. And I think part of the reason was because I thought in terms of a mechanical situation, and I was trying to apply it to an electrical situation. In other words, if I have a stack of pallets, okay, and I put 5 pallets in the bed of my truck, okay, I've created a load in my truck. It's not a very big load, but I've created a load in my truck. If I put 5 more pallets in my truck, I've created an additional load in my truck. If the pallets all weigh the same, which they usually don't, but let's assume they do, I've doubled the load, haven't I? Okay? And then if I put, another 10 pallets in my truck, I've doubled the load again. Okay? Now, in electrical circuits, for most hookups, which are what we'll learn later to be parallel hookups, it's just the inverse of that. In other words, let's say I had a hairdryer. I take a hairdryer and I plug it into the receptacle in my bathroom. Okay? That receptacle in my bathroom is connected through the wiring in my house and ultimately to a breaker in my panel. Okay? So now let's say that I come along and I put a second hair dryer into the receptacle. Okay? What have I done to the load? Well, I may not have overloaded it. It depends. What if I have a 600 amp main? And let's say that breaker is a 60 amp breaker and that the hair dryer, is only 1500 watts. I haven't overloaded it. Okay, but I've doubled it. Exactly. I've doubled the load. Okay? Now, let's assume for a second that I pull those out and I put a surge suppression strip, like you plug your computer into. So there's multiple receptacles. Okay? And I plug my 2 hair dryers back into the receptacles in the surge suppression strip. Okay? And then I put another hair dryer into that surge suppression strip. What have I done to the load?
Tripled it. Triple?
I've tripled the load. I've increased it. the load has gotten bigger. The load has gotten bigger. Okay? And then on and on and on. If I put a fourth hairdryer into the receptacle, right? Now I have even more load. Okay? As the weight in my truck increases, it goes up as I stack pallets in my truck. Okay? The resistance in the bathroom as I plug in successive hair dryers goes down. Whoa! What do you mean down? How could it go down? If I plugged more hair dryers into the receptacle, how could my loading on my panel, where my breakers are, go down? Well, as we will learn, the reason that it goes down is because resistance is an inversely proportional relationship. In other words, we find it in the denominator of a fraction. And that's something that, to tell you the truth, it took me a while to come to grips with it. Because I'm thinking, hey, if I add more and more and more and more lighting, or more and more and more and more hair dryers, or more and more whatever electrical appliance, I'm increasing the load. I'm not decreasing the load. And then if I think of, a mechanical analogy, like putting something in the bed of my truck, the load's getting heavier. The springs are compressing. I'm reaching the maximum load at some point of my truck. Okay? But when we start talking about resistance in an electrical circuit, what we find is that when resistors are connected the way that they're connected probably about 98% of the time, which is in parallel, which we'll talk about later. Okay? It turns out that every time we add another successive load, the resistance, or remember our mantra yesterday? What is resistance? Opposition to current flow. That's what resistance is. Opposition to current flow. The opposition to current flow doesn't get bigger, it gets smaller. Okay? Now, yesterday we talked a little bit about what resistance is, and I'll just briefly review that with you. If you recall, we talked about the analogy I use every semester, and that's the swimming pool, right? If we go over to the Cuesta College swimming pool, and the swimming pool's dry, and I walk 5 feet through the swimming pool, there's basically very little opposition to my attempt to move through the pool, right? Because the only thing that's blowing against me is air. But on the other hand, if the swimming pool is filled up to my waist level with water, and I attempt to walk the same 5 feet, is the opposition to my movement through the pool the same or different with the water in the pool? It's different. Did it get bigger or did it get smaller? Bigger. Got bigger. I mean, anybody knows who's been in a swimming pool that if you're trying to walk through water at waist level, you got to use more energy. You got to use more muscle. Okay? Now, the other thing that we talked about was replacing the water in the swimming pool with something that had a high viscosity. Okay? If we replace the water in the swimming pool with, let's say, gear oil, 90 weight gear oil, is there going to be a difference between my opposition to moving through the pool 5 feet with the water and the gear oil, or are they going to be the same? Different. Okay. Same thing in electrical circuits. Depending on what is in the electrical circuit, Is it a resistor? Is it parallel resistors? Is it series resistors? Are there inductors? Are there capacitors? Are there semiconductor devices? The list goes on and on and on and on. But depending on what is in the circuit and how it's wired together, the opposition to current flow is going to change. Okay? And that opposition to current flow is something that we find in a great number of the formulas that we're going to deal with, starting with Ohm's law. Okay? The most popular formula from Ohm's law is the formula that says E equals I multiplied by R. Voltage is equal to current times resistance. Okay? So let's say that I had a battery, and the battery was a 12-volt battery from Walmart. Okay? And I took that battery and I hooked that battery up to a hairdryer. And I'm going to represent that hairdryer by the resistance that's in the hairdryer. There are also other electrical quantities or components in the hairdryer. There's inductance in the hairdryer, not much capacitance, but there's inductance. But there's resistance. And resistance is the only thing that we're going to study that dissipates heat, that gets hot. Okay? Inductors don't get hot. Well, ideal inductors don't get hot. And ideal capacitors don't get hot. They still require energy, though. Okay? If, for simplicity's sake, let's say that this hairdryer right here had a resistance. And what is resistance? Opposition to current flow. Just like walking through the pool. Okay? But instead of a human being walking through the pool, what's happening in an electrical circuit? What's moving?
Electrons.
What kind of electrons? Valence electrons. Valence electrons. Valence electrons are the electrons in the outermost shell of the atom that you're dealing with. Okay? Conductors are atoms whose valence electrons are easily moved out of the valence shell. Insulators are atoms whose valence electrons are difficult to move out of the valence shell. Okay? So let's just say, for simplicity's sake, that the resistance of this hairdryer was 12 ohms. In reality, it's not going to be 12 ohms. It's going to be more than that. But let's just say, for simplicity's sake, that we found one, or we could make one that was 12 ohms. Okay? That was 12 ohms. And we wanted to know how much current was flowing in this circuit. Now again, when I ask you what current is, what type of current are we going to be focusing on in this course? Two different types of currents that are studied in the study of electrical engineering technology. Okay? One of them is electron flow theory, and the other one is conventional flow theory. Okay? The only difference between electron flow theory And conventional flow theory is which terminal the electrons leave in a battery. In electron flow theory, which terminal do the batteries, do the electrons leave the battery? Negative. Electrons leave the negative terminal of the battery. Okay? So this is what we are going to study, and this is what is emphasized in our book. The only reason that I mention this is because in some engineering schools they use conventional flow theory. Okay? It's wrong from the standpoint that the valence electrons are not moving this way. They're not moving out of the positive terminal. Okay? But if a person makes a statement that we're going to call this a negative current, in my mind, they've added complexity to the circuit that's unnecessary. Okay? But theoretically, there's nothing wrong with it. Okay? When you get into semiconductor studies and the movement of holes, there is some argument for the movement of positively charged particles. Okay? And that's one of the reasons that the engineering schools stay with conventional flow theory. But when you're talking about a hairdryer hooked up to a receptacle in a house, okay, you don't have holes moving. Okay, unless you have a hairdryer that's got some real sophisticated semiconductor components. Now, in this circuit right here, assuming that we're using electron flow theory, which is what we're going to use from now on, and the only reason that I mention this to you is because if you're working in a group and the group consists of electrically trained people that have gone to programs like this, people from the Navy who also study electron flow theory, and also engineers who have gone to ABET accredited engineering schools, then you're going to have a mixture of people who have been taught two different ways. Some people have been taught conventional flow theory. Some people have been taught electron flow theory. Okay? So if you see the person who, let's say, has an engineering background, draw this circuit or some other circuit on the board because you're doing some design work or some troubleshooting analysis, and they draw an arrow so that the current is leaving the positive terminal of a DC battery, you'll understand why they're doing that. Okay? And it's not that they're dead wrong. Okay? With a little bit of math, in other words, all they have to say is, yeah, that's a negative current, which changes the direction of the arrow. Okay? So it's not that they're wrong, it's just a tradition. It's been handed down for over 100 years. Okay? Now, using electron flow theory, we know that the electrons are going to flow out of the negative terminal of the battery. Okay? If we were to apply the most fundamental equation from Ohm's law to this circuit right here, and we wanted to know what the voltage drop was going to be across this battery. In other words, if we took a digital multimeter or a voltmeter and we hooked it up right there, and we wanted to know what the voltage drop was going to be across that resistor, could we use that formula to figure it out? How would we do that? Well, right now, what is it that we know? We know the voltage across the source, and because there's only one other thing in the circuit, later on we'll learn a law called Kirchhoff's voltage law, and that'll tell us that the voltage has to be the same here as here. Okay? But for most people, it's kind of common sense that if you only have two things in a circuit, an active source, like a lead-acid battery, and a hairdryer or a resistor of some kind, they're both going to have the same voltage on them, right? In other words, what is the voltage coming out of the receptacle in your bathroom? 110, 120. Federal law requires the voltage that comes into homes to be approximately 118, plus or minus 8%. So if some people say, and this is something that I'm asked a lot, my house has 110 volts, well, my house has 120 volts, well, what's the difference? Well, there is no difference. There is no difference. There is a difference because if you measure them, they come out different. But anything that's designed to work off of 120 volt service or receptacle or power source is going to work just as well off 110 volts and vice versa. Okay? So for practical reasons, we say there's no difference. Okay. So here, let's look at what we're given. The two things that we're given are the voltage, which is equal to 12 volts, and the second thing that we're given is the resistance, which is equal to 12 ohms. Okay? So, using logic and reasonable deduction, can you look at this and by inspection tell me how much current is flowing in the circuit? Well, let's take it a step further if we're not sure. Okay? This formula right here that we have tells us what voltage is equal to in terms of current and resistance. We're given voltage and resistance, but we're not given current. We are trying to find current. Okay? We're trying to find current. So what we have to do is we have to solve this equation for current. So for those of you that haven't had algebra in a while, we write the equation, voltage is equal to current multiplied by resistance, and then what we want to do is isolate the variable current. Isolate meaning get it alone, or get it on the left-hand side of the equal sign. Okay? So if we were to divide both sides, if we were to divide the right side of the equation by resistance, what's anything divided by itself? 1. So 10 divided by 10 is what? 1. 0.031 divided by 0.031 is what? 1. A park bench divided by a park bench is what? 1. I'm joking a little, but it's 1. Anything divided by itself is 1. So this cancels out, and this becomes 1. Okay? Now, we have performed an operation to the right-hand side of the equal sign. And the operation was to divide by r. Okay? In algebra, if we do anything to one side of the equation, what do we have to do to the other side? Same thing. So we have to divide this side of the equation by r. And that way, our formula has not changed. The look of it has changed, but its mathematical accuracy has not changed. Okay? So if we simplify this, we get E divided by R equals I, or we can move the I over to the left-hand side of the equal sign. I is equal to E divided by R. Okay, now, do we know the voltage? Yes, 12 volts. Do we know the resistance? Yes, 12 volts. So all we do is plug those numbers into those variables like a light socket. Okay? So this is equal to 12 volts divided by 12 ohms. And what do we get? 1. We get 1. And current is measured in what unit? In amps, in amperes. And a little bit further into our discussion, we'll talk about what amperes are. Okay, so are there any questions so far? Okay, so in this circuit, what we did was we gave an example of a DC power source, like you'd find under the hood of your car, lead acid battery, that was 12 volts. We hooked it up to a resistor that was 12 ohms, and we used Ohm's law, which we'll be using throughout this entire course, and I guarantee you'll be using through your entire career if you stay in the electoral fields. And then we substituted the numbers in to figure out how much current was flowing in this circuit right here. Okay? Now, can anybody tell me, question?
So resistors like a machine, like your starter on your car? Or your...
Good question. What is a resistor? And he asked, is a resistor like a machine? Well, the space shuttle, I guess, could be classified as a machine. I wouldn't call the space shuttle a resistor. You know, I'm kind of joking a little bit, right? What we do in electrical engineering technology is we refer to resistors as loads. A load is something like a light, okay, or a hair dryer, or a microwave oven, or something that you have to plug in to make work. Okay? That's the general definition of what a load is. Okay? Okay. Now, when we're talking about voltage, there are actually two different letters that are used interchangeably to describe voltage. And the reason I want to emphasize this to you early is because depending on what book you read, what article you look at, who you listen to, they may use one or the other. Okay? And so the two letters that are used to describe voltage are E, which we saw over here in our formula. Voltage equals current times resistance. That's the simplest formula for Ohm's law. The other letter that's used to describe voltage is just simply V. So some books will write Ohm's law like this. V equals IR. Okay? The book we're using writes E equals IR. Okay? Now, if you understand that these are really just nicknames for each other, is there really a difference between using V or using E? No, there's not a difference. So don't allow yourself to get hung up on that. In other words, if you look in another book or you have a manual and they use V all over the place in the formulas for voltage, and you look in the book we're using and you see that E is used in the formulas for voltage, don't get hung up on that. Just understand, it's like a nickname. Somebody, in the middle row might be named Mike, and their nickname might be Frankie. Just because somebody calls them Frankie, it doesn't make them a different person. They're still Mike. Okay, they're just used interchangeably. Did you have a question?
So why it's current or amp?
Right. It turns out that current, which is the letter that's used in the formula to describe amperes, is the only one that I've ever seen in the formulas. The letter A is the unit. Like in our book, they'll use E in the formula, and then they'll use V as the unit. And to our author, that makes better sense, because if you look back here at this formula, E equals IR. Well, E is the letter in the formula, but it has a unit of volts, or V. I represents current, right? And it's the letter that's used in the formula.
Does it stand for anything?
Yes, it does, and we'll get into that. I stands for something very specific. Okay? Stands for something very specific. I stands for, and we'll get into it, but I stands for a movement of a certain number of subatomic particles, electrons, that pass a given fixed location per second. It's kind of like water.
But it doesn't stand like for a word, like E for energy or
No.
R for resistance.
No. It's just a letter that is used in the formulas, to calculate voltages, I for current, R for resistance. Okay? And then also for R, in pretty much all the books I've ever seen, the formulas that involve opposition to current flow use the letter R to represent opposition to current flow. Okay? But the unit is in ohms. Okay? Written out OHMS or simplified by this Greek symbol. Anybody know what this Greek symbol is called? Omega. Okay? In electrical studies, there's a lot of things that are simplified by using Greek symbols. Okay? And you'll get used to that. So, to simplify this, we've talked about voltage, and we've said that voltage can be expressed as either E or V in the formulas, depending on which book you're looking at. Now, let's review what voltage is. The simplest explanation for what voltage is, in my view, is electrical pressure. It is the pressure that pushes the valence electrons, the subatomic particles that actually move through the copper or the aluminum wire or the silver wire or the gold wire. We don't have much gold wire around because it's expensive, but there's some real high-end audio stuff that uses gold connections, okay? And electrons move through that gold, okay? But it is the electrical pressure that pushes the electrons through the circuit. Now, if you were trying to make an analogy to electrical pressure in a mechanical system, let's say that you're setting up an irrigation system on a farm, what would the analogy be to electrical pressure in a mechanical system? Water pressure, like the PSI. The PSI that we find in a water system. So when you go home, if all the spigots are turned off and you've paid your water bill, so you've got water, okay, there's water in all your pipes. But none of the water is moving if you haven't turned on any spigots. Nobody's taken a shower, nobody's turned on the sink, you know, there's no water being used. But yet there's pressure in the pipes so that when you go up to turn on the shower and you turn the valve to open up the valve to allow the water to come through the pipe and into your shower, right, then it's that pressure that's pushing on the water effectively that causes the water to move through your shower head spigot and then to, you know, spray into your shower. Same thing with voltage. Voltage is the electrical pressure that causes the electrons to flow through the circuit. If this is a hairdryer, okay, and in a hairdryer generally we're going to be using an AC source. Okay, so just kind of bear with me here a little bit. We could certainly design a hairdryer that runs off DC. Okay, it's just that most hairdryers run off AC because we don't want to bring the batteries out of our car to dry our hair, right? But we certainly could design a hairdryer that runs off DC. Okay, it's the electrical pressure that pushes the electrons through the hairdryer that causes the hairdryer's motor to spin and the hairdryer to work. Okay? What is another name that is given to voltage? Another name that's given to voltage, well, let's leave that one for last. How about one that's a little bit simpler to explain? EMF. EMF, excuse me, stands for electromotive force. So that gets right back to our pressure again, right? It's the force that's pushing the electrons through the circuit or through the wire, okay? And which electrons are being forced through the wire? Valence electrons. Always valence electrons. The reason that the other electrons that are held more tightly to the atom never flow through the copper wire are because just that. They're held too tightly to the copper wire. And as a result, they can't break their bond and move through the wire. So it's only valence electrons that engineers work with. Now, if you're designing thermonuclear weapons, then you have electrons that are moving around that are non-valence electrons. And that's why you get so much energy. Okay? And then the last name that's given to voltage is what we call potential difference. And I'm really not going to talk about that much right now because it doesn't have a lot of meaning until we get to capacitors. It's kind of hard to understand. When we get to capacitors, it's going to make a lot of sense. But right now, electrical pressure is about as far as you need to go. Current in formulas is always represented by the letter what? I. So anytime that we're talking about current, we represent current by the letter I. And what are the units on current? Amps. So most people know that just from looking at specifications on cordless drills or, doing handiwork or whatever. Resistance. Resistance is what? Opposition to current flow. Why do I make such a big deal about that? Okay? The reason I make such a big deal about that is because when we get into AC, there are components in AC like inductors and capacitors that offer opposition to current flow, but they dissipate no heat. If this is a hair dryer, is it dissipating heat? Yeah, that's how it's drying your hair. Okay? But when we get into AC, we're going to come across components like coils of wire that are wound around ferromagnetic cores, okay, that offer opposition to current flow, but there's no dissipation of heat. Okay? We also deal with capacitors. They offer opposition to current flow, but there's no dissipation of heat. That's why I stress that so much. Okay? What about power? Okay? Power is measured in, I heard somebody say it, the unit of watts, right? And now comes the more physics-oriented question. What is a watt?
Rate at which energy is transferred per time.
Well, if we were talking about units per unit time, what unit per unit time would we be talking about? Joules per second. Okay, and that may be something that you heard in high school physics, and you'll read it in your textbook. Okay? Joules per second. That's what power is. Power is, what is a joule? It's a quantity of energy. So watts are quantities of energy that are dissipated per unit of time. Okay? Let's talk about elements. What are elements?
Periodic table.
Elements are the things that you find on the periodic table in your chemistry class. Big chart up on the wall. and it's got abbreviations for hydrogen, oxygen, copper, silver, silicon, whatever. Okay? It turns out, does anybody know how many elements there are on the periodic table?
Over 110. If you count the man-made ones.
Well, if you look at the naturally occurring elements, there are 107 naturally occurring elements that you find on the periodic table. And then finally, the atom. The atom is actually made up of, we talked about this yesterday, what? Subatomic particles. Atoms are made up of subatomic particles. If we use the Bohr model of the atom, the Bohr model tells us that atoms are made up of protons, electrons, neutrons. Okay? So, in an atom, it turns out that we have protons, neutrons, and electrons. If we look at BOHR, the Bohr model of the atom, which has been proven to not be 100% accurate. If you look at quantum physics and quarks and things like that, it basically can disprove the Bohr model as being 100% accurate. But for the purposes of electrical engineering technology, it's all we need. Because we don't really have a need for anything more than that. Okay? The Bohr model of the atom tells us that an atom is made up of a center core. And what is that center core called? The nucleus. It's called the nucleus of the atom. Okay? Now, what is inside the nucleus of the atom? Protons and neutrons. Okay? Orbiting around the outside of the atom, very similar to the way the Earth orbits around the sun or the moon orbits around the Earth, are the third subatomic particle. And what is that called? The electron. And that's the thing that moves through the wire that allows us to, it's part of what allows us to transfer energy. So these are electrons. And remember that it's the outermost shell that we're always interested in the study of electrical technology. It's the valence shell. Okay? Now, what is it that determines how many protons and neutrons and electrons are in a particular particle? The answer is it depends on what element it is. We said that there's 107 different kinds of elements. So if you look at the periodic table, we don't have one in here, unfortunately, but if you look at the periodic table, there's 107 different elements, and each one of those elements has a different number of protons, electrons, and neutrons. Okay? Now, there's one thing that, that I will bring to your attention. Let me draw the nucleus as a slightly bigger circle and represent an atom that's a bigger atom. Let's say that this atom had several protons in it. And it had, several neutrons in it. Before we talk about what's going on inside of that atom, let's move up here to the top of the board and let's talk about the relative charges on the electron, the proton, and the neutron. What charge is on the electron? Right. Your choices are positive, negative, no charge. I have no idea. Those are your choices. I'm kidding, right? You should have an idea after I tell you. So the charge on an electron is a negative charge. That's a negatively charged subatomic particle. So, you can make it sound fancy when really it's not a fancy thing at all. It's not really all that complex. When somebody hears the words subatomic particle theory, I'm going to take a class in subatomic particle theory. Most people get scared away. It's like, whoa. That's going to involve a lot of late nights. I don't want to do that. Okay. It's not all that difficult, especially if you're studying the Bohr model of the atom. What is the charge that's associated with a proton? The subatomic particle, a proton.
Positive.
Positive. So protons have positive charges. These are questions that you can expect on quizzes, midterms, finals. Okay? And then finally, what is the charge on a neutron? Or no charge? There's no charge at all on a neutron. Okay, so very quickly, I'm fairly certain that everybody brings to this class a knowledge or a basic understanding of the laws of repulsion and attraction. In other words, two particles that have like charges, like two protons, if you bring them close, what do? Push apart. They repel. So like charges repel. What about dislike charges? An electron and a proton. Bring them close together, what happens? They attract. Okay? And then charges that have no charge, it's not even worth talking about. Okay, so what about inside the nucleus of this atom right here? The only thing that we have are protons and neutrons, according to the Bohr model of the atom. Well, if like charges repel, then what is it that's keeping this nucleus from blowing apart? The law of repulsion says that if like charges start getting real close together, they repel each other. So what's holding the nucleus of the atom together? You have what?
Quarks, maybe?
There's various theories. One of the theories is that there's a particle called a gluon. And it acts like a subatomic superglue. And it keeps the particles together. To be honest with you, we really don't know. Okay? All right. Let's go ahead and take about a 10-minute break. And then we'll get back together and figure out what we're going to do.